These are the largest creatures on Earth that most people will never see, living in a world we've barely begun to explore. Deep beneath the sunlit surface of the ocean lies a realm of perpetual darkness, crushing pressure, and near freezing cold. And somehow, this is where evolution builds its giants. Scientists call it Abyssal Gigantism, the pattern where deep-sea species grow dramatically larger than their shallow water relatives. A shrimp-like isopod scaled up to the size of a house cat, a squid stretching longer than a school bus. This isn't a handful of freak outliers, it's a recurring rule of life in the deep, one that's shown up again and again in unrelated branches of the animal kingdom for hundreds of millions of years. To understand how the abyss forged these Leviathans, we have to go back before the giants existed at all, to a time when the deep ocean was simply an empty, hostile frontier. What happened next wasn't an accident, it was a slow, brutal negotiation between life and three forces: pressure, cold, and starvation. Each one left its mark. Together, they built monsters. Rewind roughly 500 million years to the early oceans of the Paleozoic. Life was only beginning to experiment with size and shape, and the deep sea was already there, vast, dark, and almost entirely unoccupied. While shallow waters buzzed with early arthropods and mollusks jockeying for space and food, the abyss sat nearly empty. No competition, no predators to speak of, just pressure, and lots of it. At the deepest points of the ocean, that pressure exceeds 16,000 pounds per square inch, enough to crush most surface-dwelling life instantly. But for the organisms that slowly drifted downward over millions of years, pressure was not only a threat. It became a filter and eventually a sculptor. Here's the mechanism. Extreme pressure interferes with the cell membranes that shallow water animals depend on, disrupting the proteins that keep those membranes flexible. Survival meant re-engineering biology from the molecular level up, thicker, more pressure-resistant membranes, modified enzymes that could still function under crushing weight. And it turns out there is a side effect to these deep pressure adaptations. They tend to favor larger cell sizes, and larger cells add up to larger bodies. This is the first thread in the story. Pressure did not just filter out who could survive in the deep, it nudged survivors towards size, one generation at a time, over an almost incomprehensible stretch of geologic time. As life pushed deeper, it ran into the second force: cold. Below a certain depth, ocean temperatures settle into a near constant chill, often hovering just a few degrees above freezing, all year, everywhere, with no seasons to offer relief. Biologists have a name for the pattern that emerges from this kind of cold: Bergmann's rule. It states that within related groups of animals, the ones living in colder environments tend to evolve larger bodies than their warm climate relatives. The reasoning comes down to simple geometry. A larger body has less surface area relative to its volume, which means it loses heat more slowly. In the numbing cold of the deep, that becomes a matter of survival, not just comfort. But cold does something else too. It slows metabolism down to a crawl. A sluggish metabolism means slower growth, but it also means longer life. Deep-sea giants like the Greenland shark and certain giant clams can live for centuries, growing a little more every decade, with nothing forcing them to stop. Where a shallow water animal might burn out its growth potential in a few short years, a deep-sea animal has time, sometimes inhuman amounts of it, to keep expanding. So the cold did not just permit gigantism. In its own patient, frozen way, it demanded it. Pressure re-engineered biology, cold rewarded size and patience. But the final force is the cruelest, and in some ways the most decisive: starvation. The deep ocean survives on scraps, a slow drift of decaying organic matter sinking down from the sunlit surface, known as marine snow. Food is rare, unpredictable, and often it's separated by long stretches of nothing. In an environment like that, a small body is a liability. Smaller animals burn through energy reserves faster and need to feed more often, which is a losing strategy when meals might not come for weeks. Bigger bodies solve this problem. They store more energy, burn it more slowly relative to their size, and can survive far longer between meals. So, while pressure and cold were shaping deep-sea life from the inside out, starvation was quietly running a filter on the outside, punishing smallness and rewarding every lineage that could scale up in weight. 3 forces, one outcome, repeated independently across isopods, squid, crabs, and fish that share no recent common ancestor. That's what makes abyssal gigantism so remarkable. It isn't one adaptation, it's convergent evolution. The same solution discovered again and again, because the deep ocean kept asking the same brutal question, and size kept being the answer. The Leviathans of the abyss weren't born giants. They were forged, slowly, patiently, over hundreds of millions of years, by the very conditions that should have destroyed them.